Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back again. The main topic of discussion this week is going to finish up the hydrogen atom, and what we're going to talk about is magnetic moments associated with the electron spin, with the electron orbit in the hydrogen atom, and will culminate in in a discussion of electron spin, which is an intrinsic magnetic moment associated with the electron. So this first lecture is about orbital magnetic moments, and in order to introduce this topic, I'd like to remind you very briefly of what you've already learned in your introductory physics class when you studied current flow in loops of wire. So if you have a loop of wire and you cause a current to pass through that loop of wire, then a magnetic field is created, and the magnetic field is, the direction of the magnetic field can be determined by pointing your thumb in the direction of the positive current flow in the wire, and then your fingers curl in the direction of the magnetic field. So if current is flowing in a clockwise direction, right? If current is flowing in a counterclockwise direction, then the magnetic field is pointing into me, right? That means that the magnetic field directions are defined as north pole is going to be on this side of the current loop, south pole is going to be on this side of the current loop, right? Now, if you suspend this current loop in an external magnetic field, so you have some external magnetic field that fills all space. You put this current loop in that magnetic field, right? And then you put a current to flow in the current loop. What's going to happen is the current loop is going to experience a torque. And that torque can be described in terms of a quantity called the magnetic moment of the loop. And the magnetic moment of the loop is defined as just the current that flows in the loop times the cross-sectional area A of the loop, right? So that's classically where this whole discussion, this whole lecture begins. It's a straightforward extension of current flows in loops of wires. If instead of a constant current flowing in a loop of wire, let's say you have just one charge, Q, right? This is a positive charge Q, and if that charge Q is executing an orbital motion for some reason, if the radius of that orbital motion is described by the quantity r, and if the mass m of that charge, or if the mass of the charge q is designated by the symbol m, then you can calculate the effective current that flows in this loop. The effective current is just the change in charge with respect to time. We've got a point charge q that's rotating, so the dq in this problem is just the charge q. The time interval, the relevant time interval, is going to be the period, the time it takes for the charge to execute one complete revolution. So this ratio of charge to period of the revolution of the charge, this defines the current. And then you can define the magnetic moment due to this orbital motion of the charge in terms of the current times the cross-sectional area A. That definition is made exactly in an analogy to the discussion we had with current flowing in a loop of wire, right? It's just the magnetic moment is defined as the current times the area A of the loop. So you can work this out, just some simple substitutions. And what you find at the end of the day is you find that there's an orbital magnetic moment associated with this charge motion. And that orbital magnetic moment is just the ratio of the charge q divided by 2m times the magnitude of the angular momentum L of the charge that's executing this circular motion. So the point of this discussion is there's a very tight connection between angular momentum and magnetic moments. And if you want to learn something about magnetic moments, then maybe if you can make measurements, if you want to learn something about angular momentum, then maybe you can make measurements of magnetic moments and infer the angular momentum that's responsible for producing a magnetic moment. So that's the general theme of the lecture, right? This connection between magnetic moments and angular momentum. Now, for the particular case we're considering, it's an electron that's orbiting in some sort of an orbit. The discussion that I just went through follows through exactly. The only difference is now the charge Q is minus the electronic charge, so there's a minus sign that's introduced. That gives rise to a minus sign in the relationship between magnetic moment and angular momentum. So this minus sign here just comes from the fact that the charge Q is a negative quantity. And what it basically means is that if the angular momentum due to the motion of the mass points up, then the magnetic moment that's produced by this orbital motion points down, right? So this negative sign just expresses the fact that the angular momentum and magnetic moment are in opposite directions. And the last thing I want to say is that this is a simple case where we assume the charge is a point charge, right? But in principle, the charge could have a more complicated distribution in space. And to take that into account, it's very often common to introduce a proportionality factor, an adjustment factor called G orbital, right? So this quantity G orbital is going to be used to adjust this proportionality between angular momentum and magnetic moment. And it depends to some extent on the distribution of the charge that's undergoing the circular motion in the problem. But for all intents and purposes for this discussion, we're going to expect G orbital is on the order of 1. And more often than not, we're going to just approximate it by unity. Okay? So that's the classical situation. This would be equivalent to, let's say, Bohr's model of the hydrogen atom, where Bohr postulated specific orbits, specific radii for the different quantum states. And he actually hypothesized that the angular momentum of these electron orbits were quantized, and if the angular momentum is quantized, that means that the magnetic moment also has to be quantized, okay? So, situation's a little bit more complicated if you treat the electron not as a particle but as a wave. And as we've discussed last week, the consequences of that is that the angular momentum of this wave, which is describing the electron motion around the proton, right, the allowed values of that angular momentum are just the script L times L plus 1 value. So if we want the magnitude of the angular momentum, we have to take the square root of this quantity, right? We introduce an additional factor of h bar because the angular momentum is quantized in units of h bar, or it's quantized in the units of the angular momentum are specified by Planck's constant divided by 2 pi. So this leads to a quantum mechanical definition of the magnetic moment of an electron wave in terms of the quantum number script L, right? And again, this G orbital is included just to provide a general discussion or a general fudge factor that may not be G orbital may not be equal to unity for some electron states around the hydrogen atom. It also follows that the Z component of the angular momentum for the hydrogen atom, according to Schrodinger's equation, is quantized, right? This is the quantum number m. We're going to start to subscript that quantum number m with the subscript L, right, to indicate it's an orbital quantum number, right? It also helps distinguish it from the mass of the electron, which is given by m sub e. And it's also going to help us to distinguish quantum numbers that are related to the spin of the electron, which we'll introduce towards the end of the lecture. So not only is the total magnetic moment quantized in terms of script L, but so also is the orbital, the Z component of the magnetic moment. That's also quantized in terms of this quantum number m sub L, right? And the proportionality between these quantum numbers and the actual magnetic moments, this proportionality is given by this constant E, h bar over 2 times the mass of the electron. That number shows up all the time. It's referred to as the Bohr magneton. And you can evaluate it because it's just defined in terms of fundamental constants. It's the charge times h bar divided by twice the mass of the electron. And that comes out to be about 9.27 times 10 to the minus 24 joules per Tesla. So that provides a convenient unit for measuring these magnetic moments. And the key point in this slide is that the magnetic moments, both the Z component and the total magnitude of the orbital magnetic moments, are quantized in units of m sub L and script L, as I've shown. Okay, what are the consequences of this? Well, you can go back to classical electricity and magnetism, and you can ask the question, if I take a magnetic moment and I place it in a uniform external magnetic field, what's the energy of that configuration? And the energy of that configuration depends on the orientation of the magnetic moment with respect to the applied magnetic field. It's the interaction energy. And this is the potential energy that this magnetic moment experiences when it's placed in this magnetic field. That potential energy is given by the dot product of the magnetic moment into the direction of the magnetic field. It involves the cosine of the angle between the orbital magnetic moment and the magnetic field. And that in turn allows us to specify this magnetic interaction energy in terms of the orbital, Z component of the orbital magnetic moment, right? Because this cosine of theta can be associated with mu, and that just gives us the projection of the Z component of the magnetic moment. So if you plot this interaction energy, okay, for a magnetic moment that has a value of 1 Bohr magneton, we place that 1 Bohr magneton in a magnetic field that's equal to 1 Tesla, and we ask, what's the value of this potential energy? What you find is, classically, you find a curve that's given by this blue line. It's just this cosine theta, where I'm varying the angle between mu and b here, right? So depending on how the magnetic moment is oriented with respect to the magnetic field, the energy of that magnetic moment varies with the angle theta, is indicated by the blue line. So classically, all values of theta are allowed, and that's why there's a continuous curve that's plotted. Quantum mechanically, though, right, there's only discrete values of the magnetic moment in the Z direction, right? Space is quantized, right? The angular momentum is quantized. And that gives rise to just discrete values for this, this potential energy of interaction. So there's a big difference, right, between the classical expectation, which is continuous. There's you can define the interaction energy for all angles. There's a big difference between that and the quantum picture, which says that there's only certain values of the magnetic moment which are allowed. Those values are determined by that parameter script L, which in turn determines the parameter m sub L, and that gives rise to these discrete values, okay? Again, if you want a three-dimensional picture of the magnetic moment problem for an electron in a hydrogen atom, you end up by using a picture somewhat similar to this. Right, this is the prediction for script L equal to 2. Right, the length of this magnetic moment here, the magnitude of the magnetic moment, is again given by the square root of L times L plus 1 times the Bohr magneton mu sub b, and then the projection, right, the projection of this magnitude onto the z-axis, right, can only have certain values. These certain values are determined by the quantum number m sub L, and that gives rise to these discrete values that project back onto the z-axis. And this basically is the space quantization argument, right? You can no longer have a continuous range of magnetic moments along the z direction. Instead, you just have quantized values that are determined by the parameter m sub L, okay? Now, how would you know that this prediction is true? If this is the conclusion that comes out of Schrodinger's equation, how experimentally would you even begin to test this idea? And that was a big problem, right? It was a big problem in the late 1915, from like 1915 to 1925. There was a lot of discussion about how to check this out. And the experiment that finally was performed that proved that this picture is correct was basically measuring forces on magnetic dipoles, right? So I have to remind you very briefly about the classical force that a magnetic dipole experiences, right? So the first thing I have to tell you is that if you take a magnet, right, a classical magnet, and put it in a uniform magnetic field, there's no net force on that magnet. It'll torque, it'll twist, it'll try to align with the applied magnetic field, but it will experience no net force that will drive it up or down. Instead, if you want to exert a force on a dipole magnet, classically, what you need to produce a magnetic field that's non-uniform with position. And so I just go through the classical calculation here. I say the force is minus the gradient of the interaction potential energy. This is a formula that you'll remember from the first week of lectures when we reviewed classical mechanics, right? The gradient operator is given by the term in the square brackets. The interaction potential energy for a magnetic moment in an applied magnetic field, that was given in the previous slide, right? It's just given by this expression here, right? So it's a dot product between mu and b, so there's three terms. Each term expresses the contribution to the x, y, and the z direction. So this is a complicated expression, right? In principle, it involves 9 different terms, right? Simply because the magnetic field in the x direction could vary with x, the magnetic field in the y direction could also vary with position x, and the magnetic field in the z direction could also vary with the position x. So this one term operating on this scalar quantity here gives rise to 3 contributions, and likewise you pick up 3 more for each, for the derivative with respect to y and a derivative with respect to z. So the full evaluation of this is rather complicated, but experimentally you can do things, right? You can make the magnetic component in the z direction much, much greater than the magnetic field component in either the x or the y direction, right? So experimentally you can achieve that. That basically means you can neglect the first 2 terms in this expression, and you're left with a force that can be approximated by this equation. And then you can further make the way the magnetic field in the z direction varies with respect to x and y. You can make that very small with respect to the variation of the magnetic field in the z direction with respect to z, right? So if you make that, if you cook up an experiment where these conditions are satisfied, then you're just left with a net force on the magnetic moment, and that net force is related to the magnetic moment, the magnitude of the magnetic moment, times the way the magnetic field changes with z, times the cosine of theta, where theta is now the angle between the magnetic moment and the B field, the applied B field. So, to make a long story short, if you produce a magnetic field that's got a gradient, the magnetic field varies predominantly in the z direction, where the z direction is pointed up. And if you insert magnetic moments with different orientations, depending on the orientation of the magnetic moment, right, you'll either get a net force that points up or a net force that points down. And if you want to know how big those net forces are, you've got to know something about how the magnetic field changes with respect to z. So this is something that you can control experimentally. And you got to go back and you've got to then evaluate the net force in terms of this equation, right? So that's the program. So classically, what would you expect if you took, let's say, a source of atomic hydrogen? So you take hydrogen gas, let's say you put it in an oven, you put a small hole in the oven so that you get hydrogen gas atoms coming out in all directions. You collimate that beam of hydrogen that diffuses out of the oven. You collimate that with a narrow slit, and then you pass it through a magnetic field that's been tailored to produce a magnetic field gradient in the z direction. So z is the direction that's pointing up and down, right? So classically, if these hydrogen atoms don't have quantized angular momentum, they will not have quantized magnetic moments. And so classically, then you would expect to see a continuous range of forces exerted on the hydrogen atoms. The forces that are exerted are strictly due to this magnetic interaction of the dipole moment with respect to the applied magnetic field. And by measuring, let's say, the maximum and minimum, right, the zero deflection, the maximum deflection in either direction, by measuring that, knowing the geometry and controlling the dBz, dz, by tailoring the magnetic fields, you can work backwards and infer something about the magnetic moments that the hydrogen atom has, right? But classically, the important point is, there should be a continuous distribution of hydrogen atoms hitting the screen due to the force exerted by the magnetic field on the dipole moment, right? So, before this quantum theory was developed, most people would say, yeah, this is what's going to happen. There's nothing interesting, nothing strange about it. Unfortunately, experiment didn't agree with expectation, right? So the critical experiments in this area were done in 1921 by two German scientists, Stern and Gerlach. They eventually won the Nobel Prize in 1944 for their work. It turns out they actually used silver atoms in these atomic beam experiments, they were able to interpret their data and show that the magnetic moments of silver atoms were in fact quantized. Rather than refer to their original work on silver atoms, I'd like to just discuss the experiment that was done in 1927 at the University of Illinois in Champaign-Urbana. These two guys, Phipps and Taylor, basically used an atomic hydrogen source rather than a silver source, and that's a little bit more relevant to the discussion in this lecture. So what they did is they produced a source of hydrogen atoms. The temperature of the hydrogen atoms was about 660 degrees Kelvin. They let the hydrogen atoms that came out of this source pass through a narrow slit. According to the theory, the magnetic moment in the z direction was going to be quantized in terms of the Bohr magneton, right? The quantization number was m sub L, but these hydrogen atoms coming out of the source were in the ground state, right? The ground state implies that the quantum number n is equal to 1, script L is equal to 0, m sub L is equal to 0. So that just simply means that the magnetic moment of these hydrogen atoms should be 0, and that just means that if they put the beam of hydrogen atoms through this magnetic field and watched how the hydrogen atoms struck the screen, right, they should get just a single line with no deflection, right? And the reason there would be no deflection is because the magnetic moment in the z direction would be precisely 0 because the hydrogen atoms were in the ground state. So that was the prediction that everyone expected. Of course, experimentally, what they observed is they observed 2 lines, right? So instead of seeing this single line, which would represent no deflection, they actually observed 2 lines, right? And in fact, when they made this magnetic field gradient go to 0, when they took the magnet, moved it away from the beam, right, then they did in fact see a single line that came through, right? They put the magnetic field back in, this single line split into 2. And so the only way you can explain that is to recognize that this simple theory based on the orbital magnetic moment has to be corrected, right? You got twice as many lines as you expected. That means that something here is wrong. And the thing that they realized is that the electron in and of itself has an intrinsic magnetic moment. And this intrinsic magnetic moment is attributed to the spin of the electron. And the picture that's emerged now is that the electron can either have a spin up or a spin down intrinsic to it. The spin up has got a z component of the magnetic moment, which is plus h bar divided by 2. The spin down has a z component, which is equal to minus h bar divided by 2. So these are the spin up and the spin down, right? The magnitude of the spin for the electron is just given in analogy with the discussion from angular momentum that we discussed last week. It's just s times s plus 1 square root times h bar. S is equal to 1/2, right? That's the magnitude of this intrinsic spin that's associated with the electron, right? So this is the picture, right? The fact that you can have spin up and spin down components for the intrinsic magnetic moment of the electron, that explains very nicely the fact that there are 2 lines observed on this screen, right? So this had to be invented, right? This was something that came out of the Stern-Gerlach experiment, which is any textbook you read talks about Stern-Gerlach experiments. It's this whole concept that they're discussing. The fact that an electron possesses this intrinsic spin means that we also have to come up with a different wave function to describe spins. And this was done in a rather ad hoc fashion. So there was an eigenvalue problem posed. You take a spin operator, the square of the spin operator, operating on a spin wave function which has a plus 1/2 h bar spin component in the z direction. So this is the spin up electron, right? That has to give you s times s plus 1 h bar squared times the wave function back itself again, right? And so since s is equal to 1/2, the eigenvalue for the square of the spin operator is now going to be just 3/4 h bar squared, right? You get the same result if you hypothesize a spin down electron state. So that's represented by chi to the minus 1/2 operated on by this operator s squared. You get the exact same value of the square of the spin operator, because when you evaluate s times s plus 1, where s is equal to 1/2, you get the same result as you got up here. The difference is in the z component of the spin, right? So this is the square of the angular momentum. This is the z component of, this is the square of the spin. This is the z component of the spin. This defines the spin up and spin down states that were required to explain the Stern-Gerlach results. So these atomic beam experiments are really important. They gave rise to these different types of wave functions that had to be invented to describe spin, basically, right? Ultimately, the spin wave functions were re-derived using relativistic quantum mechanics, but that's beyond the scope of this course. But they do come out naturally from a relativistic treatment of the hydrogen atom, but that's something that we won't get into. But right now, we just posit these spin wave functions and we try to examine the consequences. Lastly, I end up this lecture by just summarizing the main results, right? I produce a table that lists the orbital quantization numbers. They're described in terms of script L, and script L then determines the values for m sub L, right? And then in addition, there's the spin that's required. So the spin has a quantum number plus minus 1/2. The z component of the spin in the is also plus minus 1/2, right? And the magnetic moments that result from the orbital magnetic motion, from the orbital motion of the electron, and the magnetic moments that result from the spin, the intrinsic spin of the electron, are listed in this slide. And in analogy to this G orbital fudge factor that we introduced, there's an equivalent fudge factor for the electron spin, and it turns out this fudge factor for the electron spin is precisely equal to 2, and careful measurements show there's a small deviation of the value from 2, right? And that deviation is extremely interesting. It can be calculated, and the calculations match experiment, but again, that's beyond the level of this course. So I think if you understand this table and you understand how to use it, you've understood the basic points of this lecture. And what we're going to do for the rest of the week is focus on this electron spin and try to explain to you some of the consequences that this discovery of spin of an electron, some of the consequences that brings into quantum theory. So come on back and listen. It's kind of an interesting story. And we'll start to incorporate these spin wave functions now in the eigenfunctions for the hydrogen atom, and we'll show you what the consequences of that's going to be. So that's the topic of the next lecture. So we'll see you then.